experimental study of the silicon-30 P gamma for understanding nucleosynthesis anomalies in globular clusters. So globular clusters are gravitationally bound systems with up to 10 million of stars. This gives rise to this characteristic spherical shape like the cluster M13, visible in the northern hemisphere with sample binoculars in the Hercules constellation. So the densities are extremely high compared to the galaxy. And to give you an example, there would be about 13 more stars between the Sun and the closest star, Proxima Centauri. So if we were located within a globular cluster, the closest star would be at the limit of our solar system. So globular clusters orbit in the halo of spiral galaxies and are among the oldest observed objects in the universe with ages greater than 10 billion years. So that's why they were used as a proof of the age of the universe. Globular clusters are important for constraining the formation and early evolution models of galaxies. So here's the Hess-Sprung-Russell diagram for Hercules cluster, which shows the luminosity as a function of temperature, or equivalently, as shown here, the magnitude of the star as a function of its color. So this is a typical diagram for a globular cluster, populated by low-mass stars, mainly in the main sequence, and in the red giant branch, all undergoing hydrogen burning. And it was admitted that each globular cluster hosts a single cell population. It means that all stars have the same age and the same chemical composition, and it can be seen as a single branch in the HR diagram. But about 15 years ago, improved photometric and spectroscopic observation came to contradict this paradigm. So some clusters exhibit anti-correlation between pairs of light chemical species, such as between carbon and nitrogen, magnesium and aluminum, or as shown here, between oxygen and sodium. So the abundances vary with more than an order of magnitude from a star to another within the same cluster. So the typical temperature of red giants during the hydrogen burning phase, about 20 megakelvin, is too low to alter the oxygen abundance and transform it into sodium. So indeed, in order to initiate successive proton capture, the particles should have enough kinetic energy to overcome the Coulomb barrier, which becomes higher and higher as the masses of the nuclei increase. So these stars must have partially inherited their composition from a previous generation of stars called the polluters. The paradigm of the unique stellar population does not hold anymore. Studies have showed that the temperature required to reproduce these abundances is about 75 megakelvin, but the kind of stars and of the polluters remain unknown. The globular cluster NGC 2419 is a quite interesting case because we observe an additional anti-correlation. So magnesium depletion with potassium enhancement need even higher temperature to occur between 100 and 200 megakelvin due to the higher Coulomb barrier. So the mystery remains complete, and we want to figure out the type and the nature of the polluter candidate by constraining its temperature and its density. So the abundances observed in this globular cluster, NGC 2419, have been reproduced with a simulated nucleosynthesis network for hydrogen burning. So temperature and density were sampled with a uniform probability profile, and the nominal values were considered for reaction rate. So here in this figure, each blue dot represents a density and a temperature condition for which the abundances are observed are reproduced. The black tracks represent the condition for which different stellar sites undergo hydrogen burning phase, such as classical novae or massive stars, for example. So the reaction rates have also been varied within their uncertainty. This caused the temperature spread, here the delta, to increase by 70% when compared to the calculation with the recommended rates. And in order to identify the key reactions for this process, the rates of each reaction have been varied individually. This figure shows by how much the temperature spread, the delta, varies when varying different reaction rates within their uncertainties. So few proton capture contributes to this delta, but the silicon 30p gamma reaction is by far the one that expands the most the uncertainties on stellar temperatures relevant for polluter candidates in NDC 2419. It happens also that this reaction is also relevant at higher temperature for another astrophysical site, which is the type 1a supernovae. So the nature and properties of these objects are still the subject of active research, but we know that they are stellar explosions that occur mainly in binary systems with at least one white dwarf. Here in this artistic view, we saw a degenerate system with two white dwarfs. The explosion happens when the mass of the white dwarf exceeds the Chandrasekhar mass. At this point, a thermonuclear runaway happens and initiates various nuclear reactions. All the stellar matter is consumed, and there is no remnant after the explosion. So the nucleosynthesis during the type 1a supernova produced many elements around the iron peak, and it has been estimated that about 2/3 of the iron of the universe have been produced in these sites. A dedicated sensitivity study have investigated the abundances of elements produced in supernovae, type 1a supernovae, and have showed that these abundances depend on few reaction rates. So the nucleosynthesis network is simulated for supernovae conditions with a typical peak temperature of 6 gigakelvin. The rates are varied with an arbitrary factor of 10. We obtain a factor of between 2 to 8 difference in the abundances of elements with masses between 30 and 40 induced by the variation of the silicon 30p gamma reaction. So this is another good reason to investigate this proton capture. So let's know more about this reaction. At temperature rates, temperature of interest, the level in the compound nucleus, the phosphorus 31, contributing to the reaction rate are just above the proton threshold. These levels are lying inside the gamma window, which results from the competition between the Maxwellian distribution of the temperature and the probability to penetrate the Coulomb barrier. So here we see the gamma window for temperatures in stars within globular clusters, 100 and 200 megakelvin and 6 gigakelvin for type 1a supernovae. So energies are known with a precision better than 4 keV, but spin parity are for the majority of levels poorly constrained. So in this figure, we see the fractional contribution to each resonance to the total reaction rate as a function of the stellar temperature, here focused on the temperatures within the globular clusters. So the state of the art is as follows. The spectroscopic factor for lowest energy resonances at 19 and 51 keV have been determined, but for 51 and 146 keV resonances, the spectroscopic factor have not been measured and the strength have been deduced from mean reduced width systematic study. An upper limit was set for the 171 keV resonance. All this information resulted in these large uncertainty bands as we see in this figure. For higher energy resonances, at 422 and 486 keV, the strength were determined through a sole gamma-gamma measurement without an absolute measurement of the reference resonance at 600 keV, which is also crucial for the normalization at higher energy resonances relevant for supernovae. So there's a real need for a better characterization of these resonances. So the strategy is as follows. For isolated and narrow resonances, as we have here, the reaction rate, sigma nu, is proportional to the resonance strength omega gamma. The strengths depend on the resonance spin and the product of the proton and the gamma width over the total width. The resonance at relatively high energies can be measured directly. last August, we measured resonance strength by the recall spectrometer Dragon because we want an independent determination of the key resonance at higher energies, relevant for both globular clusters and supernova. But for low-lying resonances close to the proton threshold, a direct measurement becomes impossible due to the ridiculously small cross-sections. So the total width is completely dominated by the gamma width, and thus the strength becomes proportional to the proton width only. The one proton transfer reaction helium-3D is an appropriate probe. We should point out that this particular reaction have already been measured at Orsay split pole, but with low statistics and a limited resolution. So states of interest for astrophysics were not observed. That's why we performed a new measurement of this transfer reaction using the Q3D with better resolution and sensitivity. So I shall focus in the first part on the transfer reaction measurements. Helium-3D is one transfer reaction associated to the proton capture. So a proton is transferred from the beam nucleus to the core one to form the nucleus of interest in its excited state, the phosphorus 31. The emission angle and the energy of deuterons are used to determine the excited properties of the phosphorus 31 nucleus. So we measure the excitation energies and extract from the angular distribution the spectroscopic informations of the levels. So the angular distribution of the deuterons is then compared to a theoretical model, the DWBA, which assumes that the transfer is a first order perturbation, while the elastic scattering dominates the entrance and the exit channel. So the nucleon is directly transferred to its orbital, for example, here an equivalent to L equals 0, with no rearrangement of the compound nucleus. From the comparison between the theoretical and experimental angular distribution, we deduce spectroscopic factor, which describes how the configuration is close to a single particle description, as shown in this scheme, and helps us compute the proton width. The transferred angular momenta L is deduced from the shape of the angular distribution, as we will see. So the experiment was held in May 2019 at Meyer-Leibniz Laboratory in Munich at the Q3D spectrometer. So a helium-3 beam have been accelerated to 25 MeV and went through a thin target of silicon oxide enriched in silicon-30, which is a stable element. The reaction products were momentum analyzed through the Q3D before arriving to a focal plane. So the latter is equipped with proportional counters for measuring the position and the energy loss of the deuterons, and the residual energy is measured with a plastic scintillator. By combining these physical quantities, we can identify reaction products and select the deuterons that are well separated from the tritons, as we can see here. The excellent energy resolution of the Q3D let us obtain high-quality deuteron spectra. We obtained 7 of these spectra for different angles, and I show here a spectrum obtained at the angle of 20 degrees in the lab frame. So it contains bound below the proton threshold, so bound levels as well as unbound levels. And we also have large peaks from reaction induced on contaminating elements. So the phosphorus 31 peaks were fitted with the skewed Gaussians with the same width and same decay parameter for the exponential tail. The skewness is due to the optical aberration induced by the large acceptance of the Q3D. And the red curve shows the best fit. The experimental resolution achieved was 3 times better than the previous experiment. So this made the separation of this doublet of interest possible at all angles. And you could also observe low populated states of interest at 7446 and 7470 keV that are of interest for astrophysics. So we deduce from the this fits the number of deuterons for each peak and at each angle. And after normalization with respect to the beam, the target, and the angular acceptance of the P3D, we obtain the experimental different cross-sections in red dots. So they are then fitted with DWBA calculation in blue curves. These calculations include optical potentials describing the entrance and the exit channel. The entrance potential was fitted to experimental data, while for the exit channel, the global potential was used. Calculations also use binding potential for describing how the proton is bound to the silicon core. And since we perform finite range calculations, we use a microscopic overlap of Brida and al. For describing the proton within the helium-3 beam. So the theoretical curves describe pretty well the data, and we can see that the shapes are characteristic of the transferred angular momenta, very peaked at forward angles for L equals 0, for example. So the normalization factor between theoretical curves and experimental data is simply the spectroscopic factor. Since Fresco code is not stable for unbound excitation energies, the spectroscopic factor are calculated for weakly bound energies, then extrapolated to the correct energy. The proton width is proportional to the radial wave function estimated for a radius where it starts to behave asymptotically. Here for the phosphorus 30 proton plus silicon 30, it's around 7 Fermi. The proton width and the radial wave function are calculated by the code VOC4. So the overall uncertainties on the proton width are about 30% and are mainly due to the optical models used. Since the statistical errors are less than 5% and the uncertainty on the form factor are compensated with the spectroscopic factor uncertainties. For the level at 7446 keV, the fit is not that good because we lack data at forward angles. We assume two possible L equal 2 and L equal 3 based on pre-existing spin parity constraints. So once the proton width obtained, the reaction rates are evaluated based on a Monte Carlo method using the code latency, where the energies, the width, and the strength are varied consistently. Gray bands in this figure shows the 68% probability coverage from the previous study, while the blue ones are those from the present work. So experimental proton width determination of the lowest energies at 19, 51, and 170 keV enabled to reduce the uncertainties on the reaction rate at lower temperature by factor 50. For the temperature range of interest for polluter candidates in globular cluster, the rate has been re-evaluated to a higher value when considering L equal 2 for the 49 keV resonance with narrower uncertainty bands. But one must not forget that L equal 3 is not discarded, and this would induce a factor of 10 difference in the reaction rate. So the 149 keV is a key resonance, and a better determination of its spin parity is crucial. For the 418 keV resonance, we found L equals 3 value, which agrees with the strength measured directly. And thus, we confirm that the resonance do not contribute to the total reaction rates. We find a good agreement too for the 486 keV, which dominates the rates for temperature above 200 megakelvin. We can see the impact of these new results obtained from the transfer reaction on the figure of the fractional contribution. So we went from this state of the art to this new results. So we could identify and measure the main resonances contributing to the reaction rates at lower temperature. We could also observe for the resonance at 600 keV that the approximation, where we assume that the width is completely dominated by the gamma width, starts to not be valid at these energies. Furthermore, The strength of high energy resonance and especially the 486 keV have been evaluated with a single measurement, and thus we want to confirm or infirm this value. And we do this by performing a direct strength measurement. Okay, so the principle is based on the measurement of the yield of the reaction. Experimentally, it's simply the number of reactions that occur for a number of incident beam particles. It is also defined as the integral of the reaction cross-section times the density of the target through a given target thickness. The cross-section is a function of the target thickness because the energy of the particle changes when the beam goes through the target. And more particularly, for resonant reactions, when the beam reaches a resonant energy, the cross-section becomes maximum. When the target is sufficiently thick compared to the width of the resonance, the yield becomes directly related to the resonance strength omega gamma, together with the de Broglie wavelength, masses of the target and the beam, and the stopping power in the target. Lucky us, the strength omega gamma is exactly what we want to measure. Direct measurements can be performed in direct kinematics, which means that the target nucleus is heavier than the beam nucleus. This was the configuration of the previous direct measurement for silicon 30P gamma performed by Dermini with a silicon target and a proton beam. In direct kinematics, the compound nucleus remains in the target, only gammas are detected, and in order to have a proper signal over background ratio, a gamma-gamma coincidence measurement is needed. This reduces significantly the detection efficiency and relies on a good knowledge of the decay scheme and the branching ratios. That's why we chose to perform the measurement in inverse kinematics. So with a heavy nucleus beam, the momentum in the light frame is transferred to the compound nucleus that we shall call the recoils, and thus it can be detected in coincidence with the gamma rays emitted. More generally, inverse kinematics offer the possibility to use radioactive beam and gaseous targets, for example. We only need to separate the recoils from the in-reactive beam particles. DRAGON was specifically designed for this purpose. So the detector of recoil and gamma for nuclear reactions at TRIUMPH was conceived to measure the rates of radiative proton and alpha capture that are of interest for astrophysics. With the two magnetic and electric dipoles of the separator, the beam is suppressed with up to 13 orders of magnitude, with an additional 3 orders when selecting the coincidence events. This gives a yield sensitivity to 10 to minus 15. So DRAGON consists in two main parts. First, the head of DRAGON. So the beam with intensities around 10 to the 9 particles per second with few hundred keV per nucleon, with energy of few hundred keV per nucleon, enter a windowless gas target that can contain up to 7 torr of hydrogen or helium gas, equipped with silicon detectors for measuring the elastic scattering for beam numerization purpose. The gas cell is surrounded by an array of 30 BGO detectors covering almost 4 pi solid angle and works as a calorimeter with up to 60% detection efficiency and 10% resolution at 6 MeV. The fraction of the recoils is selected with the spectrometer and transported up to the tail of DRAGON. It consists in a set of 2 microchannel plates for local time of flight. Unfortunately, during our experiments, only one was available. After, the recoils enter an ionization chamber with a double-sided silicon strip detector inside. This hybrid chamber measures the energy of the recoils and gives a mean for particle identification in order to distinguish the recoils from any leaky beam. So the experiment had been done last August, where we measured 3 resonances of interest for the globular clusters, as well as 3 higher energy resonances interesting for the supernovae. The yield is, as we saw, the fraction of recalls over the number of incident beam ions, and this has to be corrected with the detection efficiency of DRAGON. I shall take the reference at 600 keV as an example. So first, we have to determine the beam normalization. The number of incident ions is proportional to the beam current over the run duration for a given beam charge state Q. But the current measurements with the Faraday cup are destructive measurements. It can be done at the beginning and the end of the run only. And in order to have an estimation for the charge accumulated during the run, we link it to the fraction of scattered beam particles measured in the surface barrier monitors and the pressure of the target. This fraction can be measured during the whole duration of the run. This figure shows the pressure variation of the run, and we see the corresponding energy structure for the scattered beams. We make sure, of course, that the conditions during the run are stable and well monitored. We can see that the pressure varies with less than 2% during the whole run. Then we measure the number of detected recalls by looking at the DSSD spectra. We can deduce the number of phosphorus 31 recalls lying within the peak of expected energy. And by gating on the correct time of flight separator, so the time of flight between the head and the tail, we can have the number of recalls detected in coincidence with gamma ray events. So in blue, we see the single measurement, and in red, we see the gamma, coincidence events in the DSSD energy spectrum. So we see that the time of flight spectrum for this reasons is beautifully clean, with very few background events. And the difference between the singles and the coincidence measurement in the DSSD is due to the gamma ray detection efficiency. So the latter is deduced from Jean 3 simulation, where the energies of gamma detected in the video array are simulated, assuming a known decay scheme. The resulting spectrum in red is then compared to the experimental one in blue, and we can see here that we obtain a good agreement, especially for energies around 6 to 8 MeV. A threshold is then chosen and set for the rest of the analysis. And the efficiency is the fraction of the simulated gamma events with an energy above the threshold over the total number of simulated reactions. The recall transmission through DRAGON is also estimated from the Geom3 simulation. For the charge state, so the charge state should be measured experimentally, but we are still waiting for some phosphorus 31 beam time. Meanwhile, the fraction is estimated with the semi-empirical formula fitted with different beams and energies. So with very conservative values, since the analysis is still ongoing and some parts still have to be done, I obtain a very preliminary value of the strength of the resonance, reference resonance at 600 keV. So the value 2 electron volt is compatible with the literature value, but the uncertainties still have to be determined. So the analysis that I showed you looks very straightforward, and it is kind of straightforward for the strong resonance. But the journey is far from being a long, calm river. For some energy resonances, the recalls are not well separated from the beam, as we can observe what we call leaky beam signature on the DSSD spectra. The simulation show also some discrepancy with the data. Here we see that the decay branching ratios that have been put are not compatible with the experimental data, and they still need to be investigated to obtain accurate efficiency evaluation. And of course, experimental conditions are not always smooth. For example, we observe sudden pressure variation due to user mishandling, especially when some shifts have to be done remotely due to COVID traveling restrictions. But nonetheless, we managed to obtain some nice data and promising results. Okay, so in conclusion, The transfer reaction silicon-30 helium-3D experiment gave us some precious spectroscopic information for the phosphorus-31 nucleus, which helped re-evaluate the strength with a better precision and hence improve the determination of the reaction rates. Furthermore, we showed the importance of the 149 keV resonance for the reaction rate at temperature of astrophysical interest, and we strongly suggest a better spin parity measurement. The next step of my work will be the completion of the analysis of direct measurement for the silicon-30 P gamma reaction, and the result will be used to further investigate the temperature conditions for polluter candidates in globular cluster NEC 2419. Finally, I want to thank my collaborators for their precious help and advice, and thank you for your attention.